everybody can see my screen?
Yes.
Good. So, hello everyone. Very warm welcome to join the keynote session of the International Conference on Applied Energy. So I'm Jianzhong Wu, Professor of Multi-Vector Energy Systems at Cardiff University. I'm Associate Editor of Applied Energy. It's my great pleasure to chair today's keynote session. So it's my great honor to introduce our distinguished keynote speaker, Professor Phil Taylor from University of Bristol. Welcome, Phil. So just to give a little bit of background info. So in 2019, the UK became the first major economy in the world to pass laws to bring all greenhouse gas emissions to net zero by 2050. It's being seen a significant step in the fight against climate change, but at the same time, putting enormous pressure on the energy system, especially when considering the energy trilemma. So obviously the planning, design, and operation of energy systems need to be revisited and optimized. So I've known Professor Taylor for over 14 years now. So Phil is an internationally renowned leader in energy systems research, innovation, and practice, who has worked in industry and academia for over 25 years. And he's the leader of several large-scale national flagship projects on multi-energy systems in the UK. Professor Taylor is currently Pro-Vice Chancellor for Research and Enterprise at the University of Bristol. So welcome, Professor Taylor, to join ICAE and meet our applied energy community. So I would like to hand over to Professor Taylor to give a keynote to share his invaluable insight and experience on planning and operation of multi-energy systems. So Phil, please.
Thank you very much.
Sharing. Yeah.
Thank you, Professor Wu, and thank you, Professor Yan, for this opportunity to speak to you all today. I will just share my screen. I hope everyone is managing to stay well and safe, and I hope you can all see my screen now.
Yeah, we can see the screen.
Lovely, thank you. So yes, I wanted to talk to you today about the potential technical, economic, and environmental benefits of multi-energy systems, planning and operation. So I will take you through that now. So just as a bit of an overview, this work is part industry, part academia, and comes from a number of large institutes like Professor Wu mentioned, the Supergen Energy Networks Hub, the National Centre for Energy Systems Integration, and these are both funded by UKRI in the UK. So first of all, I wanted to start by giving a little bit of energy systems context, and then trying to show that at least in the UK, this problem is definitely an energy problem, not just an electricity problem. And I think sometimes our community do tend to think about this too much down the lines of electricity. I then want to show you some work we've done on multi-energy systems and how we use those to try and increase the flexibility that is available to us, which is very useful in dealing with the decarbonisation challenges that we face. I'm going to talk about a little bit of modelling and simulation work first, but then I'm also going to show you a project at a site called Integral, which is where we're starting to demonstrate multi-energy systems at full scale. I'll then talk a little bit about electrical energy storage and some of the work we've done there, and then finish just very briefly telling you about an exciting new project that Professor Wu is leading and I'm contributing to, which is a UK-China project looking at urban multi-energy systems. So I hope that will be of interest, and I guess I can take questions at the end. So if I think about the UK energy sector, but also my observations here are true for many European countries and North American countries at least. And the first observation there is to say that our energy systems are really quite fragmented, and they're fragmented across many dimensions. So within the industry sector, they're fragmented very often. Companies are separated in terms of the vector: heat, gas, electricity, transport, and water. So we have private companies running different aspects of those vectors or sectors. And also even within those sectors, we have unbundling where we've broken supply out from distribution, from transmission and from generation. And this causes legal, commercial and regulatory barriers to exist for greater systems integration. And we have to try to overcome those. Even within our governments and the regulator, we see that they take siloed approaches as well. And I think, to be fair, we have to accept that sometimes in academia, we tend to work within our comfort zones and within our single vectors or technologies. And what I think is that we all need to break down those barriers and silos and start to work in a more integrated way to help us accelerate in a safe and affordable way to low carbon energy systems. And if we look at what's happening in our energy systems, we can see that we have made a lot of progress in some sectors. So particularly in electrical networks, we can see that, for example, in the UK, we're getting towards 40% decarbonisation, which is very encouraging, but the really hard work will be that remaining 60%. And also we've made very little inroads in decarbonising heat and decarbonising transport. So a lot of work to do. In terms of costs, in the UK at least, we have some very disparate findings where we have a lot of families who spend more money on fizzy drinks than they do on electricity in a year. But then we have more than 3 million people living in fuel poverty. And we see that the economic damage that COVID is having globally is only going to put more people into fuel poverty, not less. Security of supply, again, is a mixed bag where many customers see quite reliable energy supplies, but others in remote areas have quite poor security of supply. And the digitalization of energy systems, which again is a big enabler of the low carbon transition, does mean that it introduces many vulnerabilities in the energy system, and the opportunities for hackers to break in and cause major disruption on our energy systems is growing. The other thing we have to think about is that we are going to experience continued climate change between now and 2050, and therefore climate change adaptation will be important. And many of the security standards, such as N-1, are really going to be no longer adequate in the face of more severe and frequent weather events. And of course, geopolitical events continue to be a concern. So taking the UK as an example here, just to try and emphasize my point about it not being all about electricity, you can see here a graph produced by Grant Wilson that shows, for the Great Britain, it shows gigawatt hours per day of consumption of energy from 2014, to 2017. And what you can see is the red trace here is electricity, and we have decarbonized approaching 40% of that. We then have natural gas demand here, which you can see is the blue trace, which is significantly higher at peak than our electricity consumption. And then the gray curve or gray shape here, which is transport fuels. So what you can see is that over the last 20 years in the UK, we've managed to decarbonize less than 40% of our red line here, electricity consumption, and made very little impact on the other vectors. So we've still got a long, long way to go. And the other thing we can see is that this blue trace not only dwarfs the red trace, but is much more variable, much higher variability in that, which causes lots of challenges for storage. So I think looking at that, you can see that some of the ideas that were previously being promoted of energy efficiency and electrification of heat and transport, for the UK at least, would be incredibly difficult. Our grid, if put end to end, would span from here to the moon and back. And to electrify all of what we see there on that graph, we'd have to build that new network all over again with about 5 times the capacity it has now. So that's not really an option. So one of the things that obviously people have looked at smart grids for many years, myself included, to search for flexibility and greater decarbonisation potential. But what's becoming more and more obvious is that we need to take a multi-energy approach to find this flexibility and to find synergies between the different vectors to help us decarbonise. There are three simple examples here I'll run through very briefly. If we imagine we have a congested electrical distribution network, or maybe an outage in that network, and we've got lots of distributed generation. At the moment, we tend to constrain the distributed generation, either because we can't accept that energy into the network at that time, or because we've got a network outage. Now, we then try to fix those problems very often in the electrical network with electrical solutions, but often they are expensive and not the best solution. And what we are starting to explore with multi-energy systems is power to X, gas to X, and vehicle to X. So we're saying, okay, if we hit a moment of congestion, instead of paying those generators money to switch off, we could convert that electricity into hydrogen, and we could then blend that hydrogen into the natural gas network. That would protect the revenues of the renewable generator and decarbonize the gas network, which is something we're really struggling with. We can then use that decarbonized gas for transport applications, or for heat applications, or even potentially convert that back from hydrogen back into electricity, if that makes sense. And so then we've got a synergy between two networks, an electrical network that has very fast changes and storage is difficult, coupled with a gas network where the changes are much slower time constants, and there is lots of inherent storage in that gas network, gigawatt hours worth of it. If we couple those together, we can have synergistic benefits between the two, and they can help decarbonize each other at lower cost and with greater security. And often this is challenged by people saying, yes, but what about the efficiencies with all those conversion stages? And that's a valid point. But as we decarbonize further and further in our systems, we're doing that with zero marginal cost generation very often. And therefore, the efficiency is less of a concern and the decarbonization is greater concern. So if we lose some zero marginal cost generation that we were previously paying to switch off, those conversion losses are less of a problem. As I said there on the second bullet, we can use gas networks as a big gas battery for the electrical network. And as the gas system decarbonizes through hydrogen and biogas, that becomes more and more attractive. The other thing finally here, and this is where, which is in demand side response, if you only do demand side response in the electrical network, then customers have to wait for that electricity. If we use dual fuel appliances and move from electricity to gas or from gas to electricity, then we still have the effective demand side response, but the customers are still able to get the energy they need, so there's less disruption for customers. So these are three examples of where multi-energy offers greater flexibility. And what we've done in the SuperGen Hub and in SESI is develop tools that allow you to run integrated simulations between gas and electricity models. And so you have a Jacobian matrix like you might recognize in a traditional electrical model, but here you've got the coupling components shown with a red circle there between the gas and the electricity. So you can look at the interactions and interdependencies between these systems and start to understand how you can plan and operate them as integrated systems. And you can see here, for example, if we have an outage near the wind farm, as I said, instead of constraining it, put that extra power that the grid can't accept through an electrolyzer, blend that hydrogen and decarbonize gas and transport systems. Now, we have also looked at a particular case of a region in Scotland here using these tools where we have two types of storage. We have cross-vector storage, where we produce gas from power and then store that gas and blend it into the gas network as and when required. and then single vector storage here in the electrical network. And what we did is we studied a particular area of energy system in Scotland and looked at different scenarios. And what we were able to see is the value of the coupling of these two systems and the value of the storage, vector coupling storage, grows as you decarbonize. As you increase more variable generation, the value of integrating these systems grows as well. So it looks like there's quite a lot of potential. But that's just models. So what we also did is, working with the companies and organizations you can see here on this slide, we built a full-scale multi-energy demonstrator system. And the lead organization here is Northern Gas Networks. And what we're doing here is we've got 5G Internet of Things multi-energy infrastructure to allow us to monitor and control this facility. We have an electrical distribution network and a gas distribution network, real systems providing energy to real customers in the UK. And what we're doing is we are producing green hydrogen from the grid and then using that for transport and for heating in the UK. And one of the things we're doing, funded by UK government BASE, is building some exemplar homes on the integral site as well that are fitted with hydrogen cookers, fires, boilers, and metering systems, so that we can start to bring the general public here and prove the safety of these systems and help us with decarbonizing the gas grid. The other project we're doing, which is called High Deploy, and again, you can see the organizations here involved. Again, Northern Gas Networks playing a leading role. We have an objective here that you can see. What we're trying to do is get all the permits and regulatory changes to allow hydrogen to be blended up to 20% quickly into the UK's gas grids. And we are trialing it here. So this area you can see here, where the blue arrow is, that's the integral demonstrator site that I was referring to a moment ago. And what we're going to do is provide 20% hydrogen blend to all of these homes you see in this blue shade here. And that's going to happen in early 2021, and the equipment is being constructed at the moment. So this is quite an exciting real world application of what the models have told us could be beneficial. Okay, so now I want to talk briefly about some of the work we've been doing on electrical energy systems. And the way that we have approached this is to start not with the technology, but to start with looking at what the services might be that an electrical energy storage system might provide to an energy system. So asking what they're good for, rather than just thinking of them as a nice new exciting toy that we can play with. And then secondly, what we do is we say, well, look, electrical energy storage is still quite expensive at the moment. So what we need to do is stack multiple services on top of each other to get maximum value from this storage facility. And when we've collected lots of data about the markets and the behaviors of the networks, we have a big data set that we can then use to characterize those services and then couple those with Monte Carlo simulations to help us size and select the appropriate technology or blend of storage technologies to provide these services at minimum cost and at highest value. We then developed some end-to-end modeling tools that allowed us to have energy storage materials models that contained representations of degradation, converter models that allowed us to understand the temperature of a particular switch in a power electronic bridge, right through to the energy system and the market requirements, all in one integrated modeling environment. And then after we've done that, again, as usual, we build full-scale facilities and couple them to the cloud so that we can look at how you could control fleets of energy storage systems that are geographically dispersed, but with an aggregated beneficial effect. So here is an example of one of the ways that we look at this sizing, siting, and use of technology. So here we just had two services. One was the storage device operating in the store market, which is the short-term operating reserve market. And the other service it was doing was for the network operator to check that this overhead line here doesn't become overloaded. So we can run thousands and thousands of simulations using Monte Carlo simulations. And this gives us a really good feel here for the state of charge range of the storage device for these two services, the cycling, the sizes of the cycling that it will experience, the utilization, the energy throughput, and also very importantly, the annual revenue that can be generated from this storage system. This allows investors, regulators, and technology providers to design a bespoke storage solution for that bundle of services. You can also then work out what kind of lifetime to expect. So here's the end-to-end modeling that I was talking about. And so we have a model here that represents the material science and the SEI layer build-up and therefore aging. And these models here were developed by colleagues at Imperial College. We then have a detailed converter model here, and this was developed by colleagues at Oxford University. And then we have a systems model here that we developed that links to the markets. So you can look at the revenues, the system requirements, right back through into the particles of the lithium-ion batteries. And what this allows you, therefore, to look at is different ways to provide the same service, and therefore different ways to generate the same revenue from a storage device, but look at what that does to degradation, for example. So the top chart here is state of charge against time. And this is an example of where the storage device has provided exactly the same service and therefore generated the same revenue, but from a different starting point with different min and max state of charge limits and different floating state of charge points. And what you can see is that if you hold the state of charge at a lower floating state of charge, you can deliver the same service, but with a much lower level of degradation. The capacity loss here in the bottom graph is the degradation. And so that means for the same revenue, your lifetime of your storage device is extended. Now, the slightly problematic thing here is that having a lower state of charge means that you're running a higher risk of not being able to deliver the services that you contracted to deliver when asked. And so there's a trade-off there between aging and confidence in delivery of the service and generating the revenue. But again, you're allowed to therefore trade off income against aging of asset. So this end-to-end tool is very useful. Now, again, here, just to stress, and this is described in an applied energy paper, actually, as you can see here at the bottom, we then take what we develop in simulation and take it to the real world. So here you can see that this was a very early lithium-ion energy storage system here that we deployed with industry, with ABB, which was only 200 kilowatts and 200 kilowatt hours. And the simulation tools were used here. We then progressed on with Northern Power Grid to a bigger energy storage system, which you can see here, which is 2.5 MVA and 5 megawatt hours, all used for the kind of decarbonization and network protection services that we referred to earlier. And then finally here, another project that we did the modeling and simulation for, which was called Smarter Network Storage in Leighton Buzzard. And this device was 6 MVA and 10 megawatt hours. So these are real world deployments of multiple stacked services from energy storage systems. So I mentioned transport earlier, as well as another sector that we need to bridge into when we're thinking about multi-energy systems. And here is an example of a project called E4 Future that we have been carrying out with National Grid, Imperial College, SESI, and Nissan. And here the idea is that we can roll out over 1,000 vehicle to grid chargers in the UK and look at fleet vehicle operators and dispatch using a cloud platform from E.ON, dispatch these vehicle-to-grid charging points into the distribution network for localized services and the transmission network for global services like frequency response. And look at how we can do that, protecting the battery itself from degradation, ensuring the state of charge is still valid for the users to make their trips, but to give us basically a very large disaggregated energy storage facility for the UK through these fleets of vehicles. And again, there's an applied energy paper here from a little while ago that shows some of the underpinning work that we did there to understand what might be possible. And almost coming to the end now, but just to say that I'm working with Professor Wu on a project that is funded by NSFC in China and EPSRC in the UK jointly, and brings together, you can see there, 4 UK universities with 3 Chinese universities to look at urban energy systems in particular, to take a multi-energy approach to that, to look at how we can decarbonize and maintain security of supply by looking at the use of soft open points for greater topological integration in the electrical side, but also improved situational awareness and the use of digital twins to allow us to take account of and exploit those multi-energy flexibilities that I spoke about earlier. We're then looking to see if we can enable trading in those urban energy systems at a lower local level through using distributed ledger technology. So this is an early stages project, but we would hope to share findings of that in the coming months and years. So finally, I think the points that I would like to summarize is that I think that a whole systems approach is needed, that we have growing uncertainty and complexity and decentralization in our energy systems. That brings lots of opportunities, but also some challenges, and flexibility in its broadest sense, not just storage, can be used to help deal with that uncertainty and complexity. I think that it's becoming increasingly obvious that one sector or discipline can't tackle this on their own, and that demonstration and living labs are incredibly important. We've got to get out of those very important models and into the real world as often and as soon as we can. I think it's important to check ourselves and say, yes, we have had some good progress, but what got us here to that level of progress isn't going to get us there, and we're going to need new techniques to deal with the new challenges, not least low or close to zero inertia grids, for example. I would also like to stress that point again about the fact that as we move towards higher and higher levels of zero or very low marginal cost generation, we are going to have to rewire our thought processes about efficiency and losses. And again, I think hydrogen will play a very important role going forward. So that's everything I had to say. Thank you very much. Thanks for your time.
Fabulous. Absolutely fantastic. Many thanks indeed, Phil. So now I would like to open the floor to our audience. So if you have any questions to ask, please feel free to have your questions at the chat area, or you could raise your hands as well. And I will invite you to unmute yourself and raise your questions. Please introduce yourself as well if we do it in that way. So one thing I want to mention, the session will be recorded, and I hope everyone is okay with this. If you have any concerns, please let me know, okay? So I just pick up several questions in the chat area. So Professor Yan raised one question. So Phil, you have talked about the role of hydrogen in multi-energy systems. So Professor Yan just asked whether you could share more thoughts on the role of hydrogen in the future energy flexibility, such as power to X, gas to X, vehicle to X, something like that. Yeah, thank you.
Yeah, so the Committee on Climate Change in the UK estimate that the UK will be using up to 700 terawatt hours of hydrogen by 2050. So certainly for the UK, and a big part of that is our heat demand, we believe that hydrogen will be increasingly important. One of the things that I think is interesting is that people are now considering building offshore wind farms in the UK that produce hydrogen direct on offshore platforms and don't even make the conversion stage to electricity. Once we've got that hydrogen, it's very useful and very versatile. We can use it for hydrogen-powered vehicles. And there's a lot of people believe that we won't be, it's not sensible to go all electric for all transport. Hydrogen trains, hydrogen heavy goods vehicles, and long distance travelers will probably favor hydrogen. And one of the things that I think is really quite exciting, and I worked on this on a microgrid years and years ago, is the idea that if you were driving electrolyzers with variable electricity, you would be able to provide essentially a frequency control, a distributed frequency control mechanism for an electricity grid, where the byproduct is hydrogen. So if you think that people get paid to provide frequency control, electrolyzers are quite attractive because they can cope with variable electrical input. It doesn't cause them to maloperate. So we could actually use them as sinks of variable power to help with frequency control, and then take the hydrogen and use that in transport or heating applications. So we would be decarbonizing the gas grid whilst providing a frequency control service to the electrical grid. I think that's quite exciting and quite interesting, actually. And I saw that work when I worked with IFE in Norway a number of years ago in a microgrid application that we developed.
Yeah, thank you very much, Phil. And I think from what you said, clearly this is a very good opportunity for new business models as well, how to make all this working together. So that's a really exciting area. Yeah, thanks, Phil. So Hong Hui raised one question. So actually applications of electrical energy storage has been introduced. So what is the role of a thermal chemical storage in the multi-energy future?
Yeah, so this isn't an area of expertise for me, I must say, and maybe Professor Wu could help me answer this question. From what I see, it looks like we're going to need thermochemical energy storage as well as electrical, absolutely. And I think that these systems are quite important when co-located with industrial applications that might have quite a lot of waste heat. And we can certainly use those. And I think we're going to need flexibility from every vector and at all scales if we're going to get to a decarbonized energy grid. So it's not an area of expertise for me, but I certainly would say it looks like it's a valuable resource for us. Maybe Professor Wu could help me augment that answer.
Yeah, thank you. I think what you have said is, I mean, I completely agree. And yesterday we had a SuperGen Flexo Fund seminar. So that is on the thermal energy storage, the role in multi-energy. We just started. Hopefully we can share more results from that. But from that project, we not only look at the thermal chemical storage, but also, for example, phase change material as well, and hot water tank, all these different type of storage. But clearly it's a big space we could look at as well. Yeah. So next question is from Florian Kaufman. So basically this question related to the threshold of 20% of hydrogen in the gas network, Phil, you just mentioned. So the question is, if we have multiple hydrogen suppliers, so how to manage this to make sure this 20% could be maintained?
Yeah, I mean, on the one hand, that's a big challenge. On the other hand, it's a slightly arbitrary threshold because as many people will know, up until about 1970, our gas networks contained 50% hydrogen because they were using Towns gas. So I suppose it's not going to suddenly all come crashing down if we hit 21% in one particular area. But as you say, the Health and Safety Executive will hopefully soon allow up to 20%, and that will be a limit. So the way that we're doing it is that we're injecting in a radial spur of the gas distribution network on that diagram that I showed, so that we are able to monitor that spur and control the blend quite carefully. And what we do is produce the hydrogen and then store it, and then gradually bleed the hydrogen out of that storage system into the gas grid based on the measurements that we take. Now, as you say, if we get multiple injection points of hydrogen, that's going to make that more complex. And I guess that's an interesting flow control problem that is probably yet to be solved. But it's a very good point that will have to be raised. Of course, the other thing that's going to be important as well is that gas meters at the moment are flow meters, not energy meters. And therefore, if the percentage of hydrogen you've got in the gas that comes into your home is varying, so therefore is the calorie content of that gas, and therefore the energy. So we're going to have to come up with new metering solutions as well. Otherwise, we're going to end up overcharging people for the energy that they've actually received. So lots of little practical issues to be resolved. And I guess that's why I think we need to make sure we're doing demonstration projects and living labs to really learn those practical lessons.
Yeah, absolutely. So this is another quick question on this, whether it's a website for FC project, but we are developing that. So I mean, probably you could search the project name, and hopefully, I mean, within 1 or 2 months, and we will set this up. Yeah, thanks for that. Another question is from Ning Chi. So this is energy storage. So energy storage system does provide a lot of flexibility. So how to solve the security and economic problem, because it's still very expensive and also sometimes have a security concerns. So whether there's new ideas or new methods on that one, if Phil could share some thoughts on that, would be great. Thank you.
Yeah, okay. So, I mean, in terms of the economic problems, what I would say is that if you deploy storage carefully and don't think that it's just a silver bullet to solve all problems, if you look for the places where it really is economically viable and economically advantageous to all the other alternative solutions that might be available, like demand side response or physical assets like copper, then you should be able to deploy storage in a way that doesn't cause economic problems. But I understand the question there, in that often we get very enthusiastic about a single technology and think it can be deployed everywhere. The other thing is, it goes back to the talk that I gave, which is that I think that we need to think more broadly. So just because there's a problem in the electrical network, don't think that the solution can only be found within that electrical network. If the flexibility can come from the gas system or from demand response or hybrid technologies like hybrid heat pumps, then there's a very good chance that they will be a better economic solution than a single storage solution. And again, the value stacking, multiple stacking of services improves the economic situation from storage. Now, in terms of the security, if I could take that question 2 ways. One is cyber security, which is what I mentioned in my proposal. And what I would say is that myself and Professor Wu are working with the leading cybersecurity community in the UK to look at how we protect critical national infrastructure from those kinds of cyber attacks, which are very real and growing. So that's one aspect. And I would say that there are multiple vulnerabilities now in the system, and that does need looking at. The other way, I guess, that storage could affect security of supply is that its reliability is lower than conventional copper assets at the moment, and therefore you could get failures of the energy storage, the power electronics, for example. There's quite a lot of redundancy built in the cells. So if we have single cell failures, the storage systems can still continue. But more work to do, and lots of communities doing that. But we do need to all work together to make sure we're working on the things that are most important for the overall system.
Yeah, thanks, Phil. So next question is quite interesting. This is also the last one on the chat area. So this is from a different angle. So for the role of hydrogen, and if the hydrogen was produced by renewable electricity, and if we use it to produce fertilizer, and this mentioned using the Haber-Bosch process. I'm not familiar with that process, and using natural gas as well. So the question is, how do you think this will impact on the use of hydrogen as an energy vector?
So I think that's a really interesting question, and there are some tensions there, aren't there? There are a few tensions. So I guess first of all, in an ideal world, if the markets were working perfectly, which we know they often don't, then if you produced hydrogen from renewables, it would be used in the most effective place. And if the most effective place for the planet and for the environment is for fertilizers, then that's where it should go, obviously, first, before it is then used in energy. If we feel that for carbon and for environmental impact and societal benefit, that's the best place for it, then that's where it should go. But that brings you to a bit of a problem, full stop, with renewable produced hydrogen. And that is that to get to the levels of hydrogen we need just in the energy sector, never mind the fertilizer sector, is a huge challenge for renewable energy. Just because of the volumes, the capacity of renewables you can build, and how much hydrogen you can make from that. So from a selfish point of view, I can imagine the energy sector will be wanting to take all of the green hydrogen it can to help it decarbonize. So that will be in tension with the market pull for fertilizers. So I suppose what that, I think, suggests to me is that we need other ways of producing hydrogen as well as direct from renewables. And obviously we can do that through steam methane reformers, but at the moment they still emit CO2, even when coupled with carbon capture and storage. So I think there's a big challenge there for the steam methane reforming sector. Now, the other thing you can do is use nuclear to produce hydrogen. And obviously that is still very low carbon. So that's another option. And if we had large nuclear build producing hydrogen, that might mean we can service fertilizer markets and other markets as well as energy markets. But there are a lot of people working on lots of different ways other than electrolysis to produce hydrogen. I saw a piece of work from some of my colleagues at Bristol University last week, where they've managed to get water droplets that have high levels of algae in them that produce hydrogen by photosynthesis. Mm-hmm. Very exciting development. And so hopefully these new ways of producing hydrogen will develop, and then that will allow us to provide hydrogen for all sorts of sectors, even beyond the energy sector.
Yeah, many thanks, Phil. I think this answer is really great. So it's really thoughtful. Thank you. And sorry, I forgot to mention the people who read this question is Richard O'Shea. So many thanks for the interesting question. So probably all the question on the chat area. We have 4 minutes before we finish, if I may. So I would like to take the advantage of a chair to ask one question. So if it's okay. So I really, agree with what Phil just mentioned. This industry is fragmented. Now we look at multi-energy. So clearly this is some sort of a natural monopoly in each area. So my question is how to break the walls to make sure we can really capitalize the benefits of integrated multi-energy system. It would be great if Phil could share your insight on that one.
Yeah, it's a very difficult question. I think a lot of it comes down to the regulator. What we've seen in the UK, and I've been lobbying, and I know you've been lobbying our regulator Ofgem to force the energy companies to work together across vectors, and we're now seeing that. So they have to actually put in their price control documents how they are taking whole energy systems and multi-energy systems into account. So that's one way. The other thing to do, I think, is through demonstrators, show the energy companies that it can be done safely, so that it looks de-risked for them, because safety is always a paramount concern. But then something else that's more radical, and some countries around the world have, but we don't have in the UK, is multi-energy companies. So instead of having an electrical network operator and a gas network operator and a heat network operator, what about just an energy network operator? And there's an economist, Touraj Jamaz, who we've worked with in the past, uses a term called economies of scope, which I think is a really nice term. So we're all familiar with economies of scale, but economists are starting to see that there are economies of scope, and broadening the scope to energy companies rather than vector-based companies. If we can show that that has great economic benefit for society, then that will help us move in that direction as well.
Yeah, thank you very, very much, Phil. So I'm conscious of time, so we're perfectly on time now. So, and I really enjoyed the keynote and the discussion. So I hope everybody feel the same. So please join me to thank Professor Taylor again for the great talk, and many thanks to all of you as well for your participation. So I would like to close the first keynote for now. So all the best and enjoy the rest of the conference. Thank you, Phil. Thank you.
Thank you very much, everybody. Thanks for the opportunity.
Thank you. Thank you. So Professor Yang, we have a next keynote. It's in 15 minutes. Shall we take a short break? So give everybody some comfortable break, and then we'll come back again.
Yes, please. Yeah, we can have, how long? 15 minutes?
15 minutes, 15 minutes. There's my understanding, yeah.
And
okay.
If Professor Zhang already here, you can test your slides and screen share. Yeah, I already noticed.
Yeah. Hello, Professor Zhang. So nice to see you here, virtually here. Yeah, so we will formally start the section in 15 minutes time. So, so now we will have a quick break, and then we'll come back shortly. Okay, so I see everybody shortly then. Okay, bye-bye.
No. It's the same room. We will be here again.